My name is Jeff Smith. I work at the SETI Institute at NASA Ames Research Center. And basically, my job is to design data processing pipelines for NASA missions. And I was invited to come here to give an example of how human-machine teams have been used to solve some problem at NASA. And I got a great one for you here. So it has to do with this tiny problem we have of finding planets 600 trillion miles away from the Earth. And it's actually more difficult than it sounds. So you may have heard of the Kepler mission. It was launched in 2009, and it's been immensely successful. The point of the mission was to search for extrasolar planets, planets orbiting other stars. And due to Kepler, we have a revolutionary view of the cosmos. We now know that planets are everywhere. There are more planets in our galaxy than there are stars. And not only that, Kepler was searching for Earth-like planets, and an Earth-like planet is basically a planet about the size of the Earth, and it's about the right distance from its host stars such that liquid water could potentially be on the surface. We don't necessarily know if there's water there, but it could potentially be. And Kepler has discovered that there are Earth-like planets everywhere. There's millions of them in our galaxy. There's nothing special about our Earth as far as we can tell, so maybe there's nothing special about life on this Earth either. But anyway, Kepler's no longer with us. I ran out of fuel last year, so I'm going to talk about a new mission called TESS. And it stands for Transiting Exoplanet Survey Satellite. And it was launched in April of last year, so it's been up there for about a year now. It's been collecting science data for a little bit less than a year, and has a very interesting orbit. We shot it out to the moon, and then we used this gravity assist from the moon to pull it into this highly elliptical orbit. And it's outside of the plane of the Earth-Moon system. And this orbit is highly stable. And it's in a 2-1 resonance with the moon. So every time the moon orbits once, TESS is going to orbit twice. And so it's about a 2-week orbit. And it's going to stare at one section of the sky during its 2-week orbit. And then I'm ahead of my animation here. So anyway, that's a picture of TESS right there. It's going to collect data. And then when it gets to perigee, it's going to turn around, download the data, and then go back and collect data for the next 2 weeks. TESS has 4 telescopes in it. Each one has a 24 by 24 degree field of view. And there's 4 of these stacked in such a way so that it has in total about a 96 degree by 24 degree chunk or sector of the sky that it's searching at any one time. Over the course of 1 year, it's going to survey an entire hemisphere of the sky. And then it takes about 13 sectors to do that. Then it's going to flip over and then survey the entire sky in the next year. Everywhere in blue here is where it's collecting data. That yellow spot that you see right at the top, that is the old Kepler field of view. And then in the Kepler extended mission, it looked along the ecliptic plane. So in many ways, TESS is complementary to Kepler. I should also point out that there's these 2 continuous viewing zones at the north and southern ecliptic, and it's searching for data for upwards of an entire year instead of just like 4 weeks. And that's important because we're searching for really small signals here. These Earth-like planet signals are really tiny, and so the longer you can search, the more likely that you're going to actually be able to find something. So that begs the question, how do we detect planets? In principle, it's actually pretty simple. So let me show you. So say you're looking at some star in the sky, and then there's a planet orbiting it. If you record the total amount of light, the total amount of flux coming from that star, it's going to dip down a little bit as the planet passes in front of it. This is called a transit. This is basically what we're looking for. And the planet is going to orbit around the star, and as it comes around, it's going to generate another transit signal in the total flux or light coming from the star. Different sized planets are going to cause different dips, so you can calculate the size of the planet. You can have multiple planet systems, and in fact, we found many multiple planet systems in Kepler, and that generates a more complex transit system, but we can decompose all of that and figure out what's going on. So basically, that's it. That's all we're doing. It's as simple as that. Now, if it was, there would be no reason for me to be here. There'd be no reason to work on this. So in reality, it's a little bit more complex. So now I'm going to tell you how we really detect planets. I can't give all the details, but hopefully enough to give you an idea that there's a lot involved here. So first of all, I like to start right at the beginning because people tend to forget about this. We're using telescopes. So there's an array of lenses, and then there's a CCD and a readout electronics. So you have to deal with point spread function, pixel response function, flat fielding, and gain, and bleeding and smear, and all these things you have to do with calibrating CCD images. And so I'm guessing there's people in the audience that can appreciate that this is non-trivial. So I just want to mention, don't forget about calibrating your image, because if you don't, you're not going to find anything. But for the sake of the argument, we'll just say magic. That all goes away, and we have a nice, clean view of the night sky. We can start searching. So we got to find stars to look at. And so there's an entire team, actually, that's dedicated to trying to find interesting stars. So we pick a star, and that looks like an interesting one. So we collect all the light around that star. We find the optimal aperture of all the pixels we want to bring down, and we generate this light curve. And so we want to find these transit signals in this light curve. So we stare at it. We stare at it for at least a month, maybe for a year. We bring on that light curve, and it's going to look like this. It's not what we want to see. Now, there are transit signals in this light curve. This is a real light curve, but I can't see them. I'm guessing you can't either. There's all this other crap in there. And this, unfortunately, is coming from the spacecraft. It's all instrumental artifacts, because even though we're staring at one section of the sky and have very precise pointing, in reality, the spacecraft's going like that. It's jittering around and shaking back and forth, and occasionally the pointing's off, and we've got to bring it back, and sometimes have coarse pointing. So there's all this mess in there. And in addition to that, we're staring at one section of the sky, but relative to the spacecraft, the sun is moving. So different sections of the spacecraft is heating up and cooling down. This causes thermal expansion and contraction. This causes the focal length of the telescope to change. This causes focus drifts. So you get these general drifts. You get thermal transients whenever something happens. In fact, there's a thermal transient right in the middle of this light curve. So all of this adds up to systematic issues that are sometimes thousands of times larger than the actual signals we're trying to eliminate. And that can be a problem. Fortunately, we've spent a while trying to characterize all this crap that you see in there. And I don't really have time to go through it all, of course, but basically we've developed a method in order to identify all these things and remove it, and I'll just say magic. And it all goes away, and we have a nice clean signal with the transits just dangling down, ready for us to detect. Now, once you detect these transits, you can actually find a lot of information. You can find the size of the planet, the relative alignment that the planet is with the star. You can find the orbital period, and hence the distance that the planet is from the star. And because you know the total amount of light coming off the star, you can estimate if the planet is in the habitable zone. And TESS and Kepler can't determine if there's biosignatures in the atmospheres, but we know where the planets are, and then follow-up measurements can hopefully find biosignatures someday. So we got to find these transits. Now, I have two light curves here. These are simulated. And I hope you can see the transits in the top light curve. That's pretty simple. The problem is that the interesting planets, the Earth-sized planets, generate light curves kind of like the one on the bottom. And here, I can't see the transits. I'm hoping you can't either. Well, we've developed methods over a couple decades now to identify these periodic transit signals. And so again, there's no time to go into it. I'll just say it's magic, and we can find them. And in fact, that's where all the transits are in that light curve. It's not really magic. It's actually a wavelet-based match filter in a White domain. And if you know what that is, we can talk about after class. But suffice to say, we can find these, and we can find them pretty well. So we found the planets. That's it. We found the transits. We found the planets. Not necessarily. Because even if we remove all the systematics, the stars are working against us too. Because stars are not glowing orbs in the sky. They're actually giant fusion reactors. And they're oscillating and pulsating. And many of them are giving off flares occasionally, including the sun. And occasionally a star blows up too. In addition to that, you look at the sky and you see these points of light, and in reality, a good chunk of all those stars are actually binary star systems, two stars orbiting each other. And these binary stars can generate a signal that looks kind of like an Earth-like transit. So just because you clean up the light curve doesn't mean you find a transit, you find a planet. You got to deal with all of this. There's another thing to keep in mind. Say you're looking at some star, and you look at that star with the red star on it, red cross on it, which I'm sure nobody can see, and you collect all the light from that star. But what if I told you that the aperture around that star is this big? You're not just collecting light from that star, you're collecting light from other stars and maybe even a galaxy in the background. So there's this blending issue where the data you're collecting isn't necessarily from what you think it is, and you have to disentangle all of this. So I know I went through that pretty quickly, but I'm going to summarize for you. So we can find planets and we can search for them, but only if we properly calibrate the CCD image, if we properly collect all light from each star, if we properly remove all instrumental artifacts from the light curves, if we properly account for all stellar objects around each star and know how they are behaving, and if we properly characterize all remaining noise in the light curves. Then and only then can we actually find the planets. If I haven't instilled upon you yet, this is actually really difficult. But we've been working on this for a couple decades now, and we've developed this data processing pipeline. And of course, I'm not going to go through this entire flowchart with you, but just to show you that there's a lot in this. And basically, we start with a raw pixel image, we process it, calibrate it, we remove systematic errors, instrumental effects, we search for the transiting signals, then when we find interesting signals, then we do this data validation step, which analyzes it, models it, and characterizes what this planet would be if it actually is a planet. And that's the problem here. The pipeline doesn't spit out planets. It spits out things that might possibly be planets, these planet candidates. And a human has to look at these and figure out or guess, is this really a planet or not? Is this worth my time to do the follow-up analysis to ground-based measurements and things in order to determine, can we confirm this really a planet? Because you don't want to waste your time. So let me show you what some of these higher level data products look like. Of course, I'm not going to go through all of this, but just to give you an idea what it looks like. Now this is a trivial detection. This is a really large planet. You can clearly see the transits hanging down. I'm sorry, I don't have a pointer. But if the pipeline detected that transit, and then if you phase fold at the right period, the transits line up, and if you zoom in, you can clearly see a planet. And I mean, this is trivial. We can go home if this is what it looked like. The problem is the pipeline will sometimes find things like this. And this is an obvious artifact. A human can look at that and say, no, there's nothing there. This is just instrumental. We sometimes find things like this, which I mentioned. There's these binary star systems that generate signals that kind of look like Earth-like planets. And a human can look at this and say, nah, that's nothing. So that kind of gives you an idea. But since I've already explained all this to you and you're all experts, we're now going to have a quiz. I'm going to show you some more interesting light curves that might have Earth-like planets in it. And I want you to guess as to if you think this is actually a real planet or not, and it's worth your time to do follow-up analysis. So here's one right here. The pipeline found 3 transits, and I'm sorry I don't have a pointer, but you can see the zoomed-in phase-folded light curve, and you can kind of see a dip in there. So is that a planet? Now we got to go through these quickly because this is a short talk, so you got to be on your feet here. We're going to go quickly. So it turns out this is not a planet. This is actually just a binary star system that looked kind of like an Earth-like planet. Let's look at another one. What about this one? Again, it found 3 transits. It kind of looks like a dip. I don't know. What do you think? This one actually is a planet. This is a real about 2 Earth radii planet. Here's another one. Kind of looks the same. How can you tell the difference? Is this a planet? This is not a planet. This is just random noise. This is just chance correlations of random noise. We're searching at signals that are just above the noise floor, and in some cases below the noise floor. So you have cases like this where the pipeline will find something, and there's actually nothing there. It's just noise. Here's another example. It looks just like the noise. This can't be a planet. This is a planet. Here's another one. It looks just like the one before. Well, that was a planet, so I can't possibly have two planets in the slides together. Well, I did. This one is also a planet. So here's the final one. This one shows a little bit stronger signal to it, but it turns out that this is not actually a planet either. There's a data processing artifact, and then it turns out a cosmic ray hit the CCD array, and it generated a blip that kind of looked kind of like a transit, and it confused the pipeline, and it spit this out and thought it was a planet, but it's nothing there. So the problem here is that we're generating thousands of these planet candidates that look kind of like planets, but we don't really know. And we have to throw out all the false positives and only find the interesting ones that are worth our time to do follow-up analysis. Because the follow-up analysis is expensive, we have to use ground-based measurements, and it takes time, so you don't want to waste your time on things that aren't really there. So whatever we can do to speed this up is important. And in the case of tests, we got to do this every single month. So now, the entire reason why I'm here is we're talking about machine learning and modern techniques. So how can that help us? And it is helping us. So this isn't a talk about machine learning, if you can't tell yet. This is a talk about an example case study, a case example where machine learning can actually be used to help humans discover something. So why would we want to use deep learning in a case like this? Well, it's an appropriate application. We're sifting through large amounts of data for some canonical signal type, and we're trying to find weak signals in noisy data. This is something that deep learning is good for. In addition to that, it's quick, it's systematic, it's upgradable, it's quantifiable. These are all good things. These are things that we want in a scientific study. But perhaps most importantly, it frees the humans to concentrate on the interesting things. Instead of the rote triage of sifting between crap and interesting stuff, let a machine do that and let the humans concentrate on the interesting things and let humans do what they're good at, which is creative thinking and really seriously sitting down and looking at a problem instead of just sifting through stuff. So this is, it could be very useful in many applications like this. So the question comes up, where do you put it? Where do you want to put your machine learning or deep learning or whatever it is you want to put in? Well, in our case, there's one obvious place. We have this pipeline, it generates a bunch of planet candidates, and at the end, we don't know what they are. So use a classifier, planet, not planet. If it's not a planet, get rid of it. If it is a planet, only then let the humans look at it. You don't have to stop there. You can keep on going. You could embed it inside your pipeline. And for example, when you're doing your match filter, searching for your signals, right then, pass it through a classifier, planet, not planet. If it's not a planet, keep on searching. If it is a planet, only then pass it to the last component. And that last component is really CPU intensive, takes a long time. So whatever you can do to eliminate false positives early on in your pipeline, the more efficient you're going to be, the more discoveries you're going to be. Now, some of the deep learning aficionados that may be in the audience might say, well, why are we stopping there? Why are we even dealing with this pipeline? Why don't we just get rid of that? Why don't we just take the raw data, pass it through a giant deep neural network, give it enough training data, and it'll figure it all out? There's an argument for that. You could make an argument, and there's logic there, but you got to be careful before you do something like that. And I think an easy way to phrase it is it's called the curse of dimensionality. And basically, as the degrees of freedom of a system increase, the data volume gets so big that the system's sparse. And from a machine learning perspective, that means there's not enough training data in order to train the machine, and you're just not going to get anywhere. You can't solve the system. So somehow you got to do something to get around this curse of dimensionality. And one way to do that is to simplify the data, to pre-process the data. You're decreasing the degrees of freedom, and you're making a simpler problem so that you have enough training data in order to actually do something. But the risk there is that you're losing information, you're corrupting the information as you process it, so it's no longer a pure signal. The other side of that is you just use brute force to overcome the sparsity, and you just throw more data at it, but all systems are data limited, so there's always a limit to how much you can do that. So where does that leave us? We could give our deep neural network just the raw data. There's no reliance on domain knowledge. There's no information loss whatsoever. And so we're just giving a nice clean signal, but the problem there is there's basically too many degrees of freedom. You can't train the system, and that's in fact one thing that we've discovered. So you got to do some pre-processing. You could fully process the data and then only rely on the final data products, and then you're relying hugely on the domain knowledge of the humans, and there's a lot of information loss because you've decreased all these degrees of freedom, but you have a very easy system to train. But once you do that, you don't have much for the machine to do because the humans have done all the work and there's not much left. So the solution is somewhere in between those two. Somewhere between the beginning and end, you want to apply it so that you do some initial data processing, but not too much, so that it's simple enough so that the machine could do something, but not so simple that basically the machine has nothing left to do because the humans have done everything. So, again, this isn't a talk about machine learning. It isn't really a talk about how you apply it. It's just an example, a use case. And I basically want to end by mentioning that machine learning has huge potential to aid humans. It's a wonderful tool. It can help us in many different types of problems, such as signal detection, like how we are applying it. And it's wonderful, but you have to be careful and not ignore the domain knowledge of the humans, because they have immense wisdom, and they know how to precondition a problem in such a way that you can give it to the machine. So the humans aren't being taken out of the picture here. And another thing to keep in mind with machine learning is that it takes lots and lots of data to train it. So whatever you can do to reduce that more can be beneficial. And in the end, neither the human or the machine will do the job perfectly. And it really takes the humans to decide, where do you put the machine? How do you wire up the machine? And then what degree do you actually trust the machine? And for that matter, what degree do you trust the humans? Because humans have biases and intuition, and that can be very useful, and it can help you solve problems, but it can also help you miss things. And there can be cases where a human will look at some data product in our case and say, that's not a planet, that's something else. And it turns out it really is, and the humans have ignored something that some AI could possibly discover that the humans just kind of basically ignored. So when you do make these decisions, it's the humans making these decisions, please use some type of quantitative objective figure of merit in order to make this decision. Because don't just rely on your gut feeling, because your gut feeling could be wrong. And there's plenty of examples in physics where human gut feeling is actually wrong, so you shouldn't rely on it too much. So basically, on that note, I'd like to end. And I'd like to thank you very much. Hopefully this was an entertaining talk for you, and thank you for your time.
Thank you very much, Jeff. I think the question that we have now is taking from the outside of the Earth to the Earth. What do you see as the partnership? What are you looking forward to most at this conference with collaboration, with talking with others within the geospatial intelligence field?
Yeah, so I mean, a lot of science and industry does become quite compartmentalized. And I originally actually come from accelerated physics. I have a degree in physics, not in astrophysics. And so I've already switched degrees once. And the team that was brought together to develop this pipeline tried to, the guy who put it together specifically tried to find people from different fields, because we all have different experiences. And again, intuition and biases, which can be good or bad. But if you put people together from a diverse background, it can really help. So when I heard about this and I was invited to come, I jumped on it because I wanted to hear people that do different things. I'm always staring out in space. I'm never looking at the Earth. So I want to talk to people that actually look at the Earth. So
That's wonderful. Well, please, everyone, again, thank me for having Dr. Smith here.